Hello, everyone. So the story for this talk started basically back in summer. I was interning at Next Silicon in Zurich, and our grand task was loop optimizations. The big problem with loop optimizations we had, well, our IR roughly looked like this. We had a control flow graph. And I don't know about you, but I have a really hard time actually finding the loop in there. We actually need to like as a human, we have to check, okay, where do these branches go? Where's the basic block? All these things. Actually finding the loops in there is not that trivial. So how do, for example, people in LLVM solve this, right? They have loop analysis. So, but like loop analysis, we heard about the analysis. No one seems to use them in MLIR. Why is that? Well, they're not that great, actually. First of all analysis, they might be invalidated. Like even during a transformation, just doing some simple transformations on your loops or whatever, your control flow can easily invalidate these. If they're invalidated, you have to recompute them in the next pass. Like in most passes, invalidate most analysis unless they explicitly preserve them. Then the loop analysis doesn't actually canonicalize your loops, right? Analysis, they don't modify your IR, and they don't ensure that your loop is in a canonical shape that is useful to your transformations. Like in LLVM, for example, there's a specific phase for loop optimizations, and in their phase, they need to ensure that their loops are in a canonical shape. They use like a loop closed SSA form, for example. Also, at the same time, the loop analysis doesn't make the actual implementation of the loop transformations a lot easier. At the end of the day, if you're an LLVM or like a control flow graph like you see here, you're still working with the branch operations that just implicitly form the loop. You don't actually have a loop construct. Well, in MLIR, we have something better, right? We have like the STF dialect. So let's maybe look at how people work with structure control flow and the STF dialect. So here you have this simple example. This is semantically actually the exact same code as you saw previously. But now I think we can all agree that it's a lot nicer to see the operations and what they're actually doing. So the first notable thing here is definitely that we have dedicated operations. Here we have an STF file, where we have like a before region and an after region being executed. And we have an STF if, where you can nicely see this is the true region and below is the else region. Having dedicated operations has a lot of advantages. So first of all, we have a trivial traversal. We saw today in the keynote, right, that if you have like loop operations, it's very easy to find them and also very performant. If you have to always perform loop analysis, which needs dominance info, finding your loops is very difficult and hard on compile time. Here we can just do a normal walk of the module, find our SCF file up, and then do our transformation that we want. We also have a trivial contain, so just finding out whether an operation is within a loop is just walking to the parent operation, checking if it's a loop op. Next, a notable difference to compare to a control flow graph, for anyone not familiar, is that we have basically region successes. That means that the control flow is not between basic blocks, but rather the control flow is between the regions of the operation, going from the parent operation into a region or from a region out of the parent to the next operation afterwards. So for the STF file, this is rather trivial, where we go into the loop body. Depending on the condition, we either leave the STF file or go into the after body. From the after body, we have our back edge to the entry to the before block. For the STF if, it's even simpler. We just go to either of the two regions and then exit to the next operation after the STF if. Then we have a constraint that, at least currently in MLIR, that everything is single entry and single exit. This is actually quite nice in terms of dominance. We don't need to do complicated dominance computation, since we have trivial dominance of any operation that comes after the loop being actually after anything in the regions, and anything before the loop actually being before the loop. Then single backedge, as I noted, this might be useful for trip computations. And data flow, we have explicit operations. Well, we first have region dominance, the normal one, so we can use any SSA values that have been defined prior to the regions. And we have explicit arguments and operands and results. So for the SCF while here, we have a block argument. This is the %eta here, initialized with an init argument. The SCF condition also takes operands. These are forwarded to the after body in the case that the condition is true. in the case that the condition is false, and the after body also goes back to the ether loop. And in the condition, if the condition is false, it turns to the result ops. Having these is actually really nice because these kind of mirror back in our C++ API. So slightly simplified slide share, the while op, you see we have nice APIs. We can just call get condition op and find the SSA value that is our loop condition. Get results for getting our loop result. Get inits, all these nice APIs that are a big improvement over the branch ops that we usually have otherwise. So ideally what we would want is an API that takes our control flow graph and turns it into a structured control flow for any future operations. Now, before going deep into that, you might be wondering, why would you even be in a control flow graph, right? Well, the obvious situation is that your input language is a control flow graph. So if you're lifting from LLVM IR, SPIR-V, or maybe some bytecode like the one from CPython or Java Virtual Machine, these all represent control flow as a control flow graph. So if you want to do any non-trivial transformations and you would like to do them in the structured control flow, you would need a lifting pass. At the same time, I would argue that for a lot of normal input languages, so traditional programming languages, for example, contrary to popular belief that ML and MLIR doesn't mean machine learning, it might be easier to actually just lower to control flow graph and then lift this to structured control flow. And an important thing to realize in this case, I think, is that lexical nesting, as you might know from C, Java, or whatever programming languages, is not actually equal to like control flow nesting. A simple example of this I have here on the right. This is just normal C or C++ code. And there's a few things we can notice. And the big issue is really stuff like break, continue, return. So first of all, this loop actually has lexically nested. We have these two blocks that end with a break and a return. But really from a control flow perspective, these are not part of the loop. These are exiting, or these are exit blocks. But at the same time, arguably, well, then we also have multiple packages. Any continue is a package. And the end of the for loop is also a package. So we don't have a single package as we would need in the STF while. And arguably, all these conditions, they're kind of like a loop condition. Like, we cannot just use an STF4 and say I goes to n. No, we have multiple loop conditions, actually. And I haven't even mentioned goto yet. So now let's get to the actual implementation of the pass. So the pass I implemented, it's actually an implementation of a paper from 2014. The paper is relatively nice, and if you want to like look into correctness details and all of these things, they prove how it works and why it works. Relevant for me was the algorithm itself. So the one nice thing about this paper, in my opinion, is that there's actually no code duplication. So none of the code that you see in the basic blocks in your input code will be duplicated in the output. There have been many papers through the years that try to do a similar algorithm of lifting things to structured control flow. Some do code duplication, this one doesn't. Then it can actually handle arbitrary control flow. So there aren't any cases of like special control flow shapes like irregular control flow that it cannot handle. It's completely dialect agnostic, the implementation that I made. So I've been showing it with the CF and the SCF dialect, but this is just because people are familiar with these two dialects. The actual implementation doesn't depend on any specific dialect, and there's an interface that you can just implement and choose your control flow dialect and your SCF dialect that you want to use for custom operations. Yeah, the whole thing is upstream. So as the driver, this is what you would use if you want a custom dialect. Or you can just use the built-in CF to SCF pass if that happens to be the dialects you're using. The only thing I needed to extend from the handle is basically block arguments handling and handling how to deal with multiple return-like operations. These are not discussed in the paper. Let's look at the top-level loop. So this is pseudo Python code or Mojo code, if you like. Essentially, the algorithm is like a recursive one, but I like personally the work list formulations. So we start with a work list, or before that, we do a consolidated return like, which I'll get to shortly. The main core of the algorithm is that we have a work list where we have always any region entries. We start with the entry of the region where all the operations and the control flow graph is contained that we want to lift to structure control flow, and we just always pop from this work list and simplify that region. An important invariance for our whole algorithm is that any region that we're currently processing will always be the entry into this region. So dominate all blocks within the control flow graph that we're trying to simplify. There are basically two steps for the simplification step. The first one is where we will transform any cycles to do a do while. After this is done, we basically have directed acyclic graph. And with this directed acyclic graph, we will then simplify the branch ups within this directed acyclic graph until we're in a structure control flow representation. Any of these steps might spawn, quote unquote, subregions that need further simplification. So this is the kind of recursion part. A good example, for example, is with the cycles where after we've lifted a do while, we might also need to further simplify any branches within the loop body. This is how we handle them, and these would get returned by these APIs. So very shortly, let's look at the return likes. You can have multiple return operations in MLIR. You don't have to have like a single return, single exit. The return like basically is very simple. Just checks for any equal operations like the two returns here and turns them into branch ups to a single block so that you only have a single return in your whole function, basically representing this whole thing as conditional flow. There's a bit of a more difficult case. Here we have, very similar to the before, but we have now a return operation, but also this exception raise operation. So two kinds of return likes out of the function. This is actually the one single case that you cannot handle with this lifting pass. This is why I call it a lifting pass and not convert CF to SCF. So if you have two regions essentially that terminate with two different kinds of return-like operations, and exactly one single control flow operation will remain in your IR. But this is luckily not that big of a deal because this control flow operations is always in your top level, not nested within any SCF operations, only nested within your func. And this is like the only such case where this would happen. So let's go a bit more detailed into the algorithm. First, handling cycles. So this is a tiny bit more complicated example in the sense that we have irregular control flow. So this is not actually a loop. This is a cycle. We don't have a single loop header, but rather two entries into the loop. The first step we do, we just find the actual cycles. This can be done very easily with the classical SCC algorithms that I think everyone is familiar with. Then we try to identify special edges. There's three kind of special edges that we need. These are the entry edges. So the entry edges are any control flow edges that go from outside the loop into the loop. Then the back edges. These are any edges that go from any block within the loop to one of the entries. And next, the exit edges. These are any control flow edges that go from within the loop to any blocks outside the loop. What we do now, and for this example in particular, is we insert so-called, what I like to call demultiplexer and multiplexer blocks, specifically three kinds. We insert a single header that turns our irregular control flow in this case to a properly shaped loop, and reroute all entry edges to go through this one header block. So now we actually have a proper loop header that dominates the whole loop. We insert a latch block, which reroutes all exit edges and all back edges to go through this latch. This latch then will perform any back edges. So now we have a single back edge, or it might go to a dedicated exit edge, which then dispatches to the original destinations of the old exit edges. So now we have nicely actually a single entry, single exit, single back edge, exactly what we need for an SCF. Now I call these demultiplexer and multiplexer blocks since they kind of consolidate the back edges, like all the edges and one control flow branch, to give you a bit more of an intuition of how these actually look like. So this is, for example, the header. So you would essentially have some kind of index value, the %dest in this case, that selects the actual entry edge that it should jump to if the header is reached. And we have all the original entry arguments, block arguments of the original entries, basically just concatenated and then forwarded to the actual entries depending on the index. Obviously, all the predecessors then have their branch operations replaced so that they choose the correct index, so that they jump to the same entry block as they originally did. Yeah, and now we have our nice SCF loop body. So this we can already lift in a do while, and the SCF loop body we then return into the work list as you've seen before. Now, handling branches. To handle branches, we remember that we have the setup of always starting from a single dominating block, so an entry block. This is our start block here, and we have arbitrary control flow afterwards. But this is already in acyclic, since we already did the handling cycle step. For branches, we now just have to partition our control flow graph for each branch we encounter into following. We partition it essentially into 4 parts. First, we have our start block. Then we have our multiple conditional regions. These just consist of all the blocks that are dominated by any of the successor edges. So here I've marked in blue and in green the two regions that are dominated by the 2 edges from start. And then we have a 4th region. This is the continuation region. This is basically all other blocks. So these are not dominated by any of the 2 edges. What we have to do now is to also get this into a single exit and single entry form. To do this, we first use the exact same demultiplexers and multiplexers block that we've seen previously. So for each of the conditional regions, we insert a single exit block. And then there might also be multiple branches that go into any of the blocks within the continuation region. So we also need to insert a single entry into the continuation. And now we have a nice single entry, single exit regions. And we can lift these 2 conditional regions basically in our SCF if or SCF switch ops. At the same time, the entry block is a dominating block for the continuation region, and the entry we just return and put back into the work list to be processed later. So I've also have a few slides with a few examples and the results. These are just taken from the test suite. So here we have a simple if case where it jumps either to the block executing test 2 or test 3, and both jump to test 4. This lifts, as you would expect, to just a nice SCF if, containing exactly the body you would expect. If we then make it a tiny bit more interesting by adding block arguments, then these block arguments get lifted to results of the SCF if that get yielded in the respective body. For a while loop, it's a bit more complicated in the sense of that here we see a bit of the artifacts from the lifting. So this is the while body, where you can see sort of from the multiplex and demultiplexer, specifically from the latch block, there's this SCF if remaining. This is basically just a missing upstream canonicalization pattern of the SCF up. So this could be further simplified. You can see that %1 hashtag 0, for example, is completely unused. But basically it has nicely the conditional structure that we would expect. Note that maybe I should have mentioned this earlier. All the SCF whiles that we do there, since we have the back edges at the bottom in the latch, we're always generating 2 while loops basically. And you can also see this with the SCF condition at the bottom, and we're basically not using the after region. It gets even more complicated when we have block args. So these go to these turn into block arguments and results and forwarded and init arguments of the SCF while. And here we even see a UB poison. This might be the case for as a side effect of the multiplexer blocks. We might need to generate some kind of undef value that gets never read for any block arguments forwarded for any cases. Then a bit more stupid examples, I would call them. So I've talked with a lot of people that have also tried to do similar things for like GPUs, where you have to often avoid the reducible loops. This is, for example, a Duff's device. It works. It's not a pretty IR, but it works. Similarly, if we have one of those multi-entry loops that I was talking about, these also work. The IR is just not pretty. But you still have the same guarantees as before that actually any CF ops will get lifted. So for custom dialects, this is the driver I was talking about. So you just call transform CFG to SCF and the region you want to simplify. You insert an instance of the CFG to SCF interface and the dominance info. The CFG to SCF interface is where actually all the operations on the dialect that you want and need are created. So the framework will basically call, for example, for just a branch example that we had, this create structured branch region up, where the important thing is here the control flow cond up. So this is where the original control flow operation would be inserted that should be replaced. So in the case of CF, this would be CF cond branch or CF switch. And the interface implementation is just supposed to return the, using the regions that are already passed to it, return the corresponding conditional region up. And then there's also for the yield ops, where you return the results. Similarly, we have for loops a create structure to while loop, where we pass in the condition, pass in the loop body, and pass in all the value ranges of like the init arguments and values that will become the block argument in the next iteration. Then my final slide, so future and enabled work. We haven't actually done any loop optimizations. So this would be the future work. What all we've done with this pass, right, is just bring our control flow into a canonical shape. So actual loop optimizations still have to be implemented. You could do further lifting, something like lifting to SCF4. So if you have an induction variable would be great. And if you're very, very ambitious, maybe even a fine or a Scala evolution. Scala evolution dialect would be nice, right? A thing I'm personally interested in would be having also a structured exception handling, but I don't think this is actually possible without the signal work that Mehdi and Jeff presented at the MLIR workshop. And I think there might be also improvements to the runtime complexity that you could make in the implementation of the algorithm. Right now, we're recomputing dominance info a lot, for example. This could probably be preserved. Thank you.
We have time for questions.
Really good work. This is really cool.
Thank you.
Question is actual loop optimizations. The IR that you get to is more structured, but it's still quite ugly. So the question is, how much power does it actually give you? Because you are calculating indices, you're doing things that normally an SCF4 will give you. And this one, like until you actually get to SCF4, there's not much more that you can do with it. So what is the objective, before you got to SCF4 with just the while? What does that give you? What is the
So at Next Silicon, we actually did a kind of case study, quote unquote, where we just tried to do like the normal loop optimization that you're used to from LLVM. And even for these, like stuff like loop unrolling stuff, you can do this on SCF while as well, and SCF if and all of these things. Just having implementing these can be done in like 50 lines of code. So just like added convenience and having trivial dominance for a lot of other cases that we had is just a huge productivity boost already. And obviously, you would want SCF4 for any serious loop optimization, let's be honest.
Yep.
But you cannot really get past to lifting to this canonical form before doing that. Like if you go direct, you cannot go direct. Well, you can probably go directly, but it's much nicer from an incremental development standpoint to first go to this to this form and then lift further to something like SCF4. If you're in this horrible situation where you need to lift.
Yeah, no, this is actually a good direction, right? It's like you do this one first because you get the initial complexity out of the way, and now you just do the SCF4 from the while.
Yes,
and
exactly.
this becomes another pass, which is independent but correlated. So that's great. Thank you.
More questions?
Yeah, there was one slide where you had poison. I think it was returned from one of the SCF if branches. I was just wondering, how did that happen? Maybe you can...
I think this is actually easier to see in the example with the header loop. So this is a side effect of the multiplexer. let's say we go from the start block and the original branch were to go to one of the entries, let's say the entry on the left. We still have the entry 2 arcs that we need to pass when we go into the one loop header though. So we need some kind of values that we pass, dummy values basically.
So these are never...
These are never read because we already know that we're going to entry 1, but we still need to pass some kind of SSA values to it, right? So this is actually a customization point within the interface. And in the lifting path for CF to SCF, what we did is just generate UB Poison because that fits nicely on our pass pipeline. But you could just generate anything, really.
Okay, makes sense.
Any more questions?
Hello and thank you. I would like to ask, like, you mentioned the work that Mehdi and I don't know the second name.
Jeff.
Jeff, yes. Jeff are doing on continue and break. How do you think that that work will affect you? And my second question would be, if you have let's say MLIR or LLVM that is produced from, or input that is produced from high-level languages that have switches, continues, breaks, exceptions, how do you think you would handle them when the signals are going to be introduced?
Good question. So personally, I'm a big fan of what Mehdi and Jeff are doing, and I would like to use these myself and experiment with them myself. I think the main, the existing lifting paths you probably wouldn't use for these, as and they're very suitable if you're, they're probably a good replacement if you're going from like some kind of input language like C. I mean, that's the use case they have, right? Jeff works at Modular and they are actually lowering the mojo to having these break and continuous. I think the main difference here is in terms of the guarantees that the ops give you. So for example, post dominance is a lot more trivial here, where you know that the loop body will be executed in full, except if you have like an infinite loop. But besides that, it will be executed in full, while with the work from Jeff or like in Modular, if you have an STF break somewhere deeply nested, you're not guaranteed to know that the whole loop body will actually be executed. You basically have a new exit block. And you also have an exit block nested within a loop, which you definitely do not hear. So it's kind of different trade-offs, different guarantees. I think for example, backwards data flow might be easy on here, but I don't want to claim that. I definitely want to get more experience with their representation. For your second question, so this was actually the use case that we have at had at Next Silicon, and why we implemented this is because we're actually lifting from LLVM. So in LLVM, these things like from LLVM, things like break, go to, and continue, these things disappear. These are just unconditional or conditional branch ups. Except with switches, there's a first-class switch up, but there's also a corresponding structured switch up. So this is not actually that big of an issue, and this is just handled by the control flow shapes. Exceptions are a lot more difficult. So structured exceptions, I have some drafts in my head how you would do these, but I don't think it would be very easy to lift this from like an invoke operation, just because of how much flexibility an invoke operation gives you compared to a structured one.
So maybe one more question. Do you think that you would be able to produce, let's say, the signals with this algorithm?
I mean, you could, but I don't think there's any point in doing so. That the signal, this is a more constrained version of the signal version, kind of. And as Mehdi and Jeff also elaborated in the talk, their signaling work is kind of a superset of this, of the structure control flow. So yeah, you could. It's just, I don't think there's that big of a point in doing so.
Okay.
Thank you.
Thank you. So thank the speaker. Thank you. Thank you.